Hey everybody, thank you for joining us for this webinar. I hope you are all safe and comfortable in your home offices at the moment. We are seriously excited to be able to present the three speakers we have from the MBTA. It's always exciting to see Elixir use cases in fundamental services and big organizations like the MBTA. So really excited to see what these guys have in store for you. Today we are joined, as I said, by three speakers who are going to be doing three distinct case studies. So as always, we will have a Q&A at the end of the session. But what I recommend you do is, if you have a question about any of the speakers' particular case studies, pop that into either Twitter or the GoToWebinar questions section when you have it, and that way you don't have to remember it for the rest of the presentation. Without any further ado, I will introduce the first of the speakers, Ryan Mahoney, who is the head of engineering at MBTA, and will be telling you a bit more about how they use Elixir.
All right, thank you very much. Today we'll be presenting Elixir and Public Transit, three case studies from Boston's MBTA. The MBTA, or the Massachusetts Bay Transportation Authority, we are one of the largest transit agencies in America. To put that in context, last year we ran about 362 million passenger trips. We're somewhat unique in that we operate multiple modes. So we've got subway, bus, commuter rail, and ferry. The emergence of new digital transit applications has increased the expectations of public transit riders for digital tools and information. Today, riders expect accurate real-time information, intuitive customer experiences, and timely communication about disruptions or changes in service. Government agencies are creating new teams that apply industry best practices to meet rising customer expectations. CTD, or the Customer Technology Department, is the MBTA's answer to this challenge. We've been around for about 5 years. We've grown from 2 to 50 people, and about a third of our team is comprised of engineers. Unique challenges require unique tools, and the Customer Technology Department uses Elixir extensively. We chose it about 4 years ago. Now we have over 20 Elixir applications running in production. That's at any given time about 60 server instances that run Elixir apps, and it's an integral part of our team culture. Shameless plug, if you love writing Elixir code for the public good, please reach out. We're typically hiring. And with this introduction, I'd like to get started with the case studies. Thank you.
Thank you there, Ryan. The first of our case studies will come from, I believe it is Paul Schwartz, who is the lead architect at MBTA. So over to you, Paul.
Thank you. Let me get my screen share. There we go. All right. Yeah, thank you everybody for joining us today. I'm Paul Schwartz. I'm the lead architect in MBTA's Customer Technology Department. And I'll be just doing kind of a quick overview of our public API and some of the features in Elixir, Erlang, and OTP, which help us build and scale it. For a little bit about me, I started in the Customer Technology Department in 2016, coming from a background building Python and Ruby applications. Kind of the first project for MBTA's Customer Technology Department was a complete rebuild of MBTA.com, the authority's homepage. We had a unique opportunity to start from scratch technically. We knew we wanted it to be data-driven so that our riders could get real-time information about their trips. We knew we needed it to scale to all of the riders across the entire footprint of the authority, and we knew we needed to be cost-effective with our resources since we're a public agency after all. I worked a little bit with Elixir at my previous job and thought that it might be a good fit for what we needed. Functional, great concurrency support, friendly syntax, a solid web framework in Phoenix, and plenty of community on both the Elixir and the Erlang sides. Elixir was also starting to get traction with some of the agencies in the Boston area. We did some initial prototypes in Python and Ruby as well, but we couldn't ignore the speed and ease of development we got from Elixir. We started development on the API in 2016 along with the website. The API provides the schedule and prediction information as a JSON API, which the website consumes. We opened up registration to the public at the end of 2017, and then later open sourced all of the code for the API under the MIT license at the start of 2019. We served 676 million requests to riders in February. That's up 10% from the month before, so we're still continuing to grow. Weekday rush hours, we see around 400 requests a second, with peaks up to 600 requests a second. Our median response time is 2 milliseconds. 99% of the requests completed under 300 milliseconds, so we're getting great performance out of the API. Where does all this data come from that we're putting on the website and in the API? There are basically two standards for transit data that my colleagues will be talking a little bit about later on. But the two that are used by kind of Google and Transit app are called GTFS and GTFS Realtime. GTFS, or General Transit Feed Specification, is for static information like routes and stops and timetables. And Realtime is for predictions, vehicle locations, and service alerts. Internally, we build this on top of the zip and GPB modules out of Erlang, as well as the EXCSV and EXProtobuf libraries in Elixir. This is one of the great features of the Beam ecosystem for us, so that we get to benefit from libraries provided by both the Erlang and Elixir communities interchangeably. So how does all of this help the MBTA? Why Elixir and not some other languages? So one great advantage for us is that it's just enough of functional programming. Functional programming is great, but not every developer or team wants to go all the way to something like Haskell or Elm. Elixir gives us most of what we need without being kind of too dogmatic about it. Since the built-in data structures, lists, and maps and tuples are immutable, we avoid the issues we were seeing in Python or Ruby, where a function modifies an argument unexpectedly or an object modifies itself behind the scenes. Immutability makes it clearer to developers what's changing and makes it easier for us to write unit and property tests around the functionality, making sure that our code is doing the right thing. Processes and the OTP model let us model separate parts of the system as if they were running by themselves. For example, in the API, each HTTP endpoint we fetch from gets its own process responsible for maintaining its own state, like caching and timeouts. If one of them crashes, that doesn't affect any of the other fetches that are happening at the same time. Each incoming HTTP request also gets its own process thanks to Cowboy and Phoenix, and none of them affect the others. Optional typing gives us some of the benefits of a stricter language, but in practice, they help us document what our functions are doing, less than like catching errors at compile time. So that's the language itself. What about the rest of kind of the Beam ecosystem? The API itself is based very heavily on Amnesia, which is distributed telecommunications DBMS, according to their documentation. But in practice, what does that mean? For us, it's a fast in-memory database. All of the schedule and prediction data is loaded into Amnesia tables for querying. And then we have some additional ETS tables for post-process data as well. In practice, what this means for us is that each API instance is self-contained. If we want to serve more queries, we can spin up new instances without worrying about overloading a downstream database. We also avoid any additional network traffic for queries as they're all served from memory. One kind of downside about this from the Elixir side is that Amnesia and ETS store their data as records or tagged tuples, whereas Elixir mostly uses structs, kind of tagged maps. There's some conversion overhead going between them. So in Elixir, we provide a simple map-based query language, similar to what clients can use via the JSON API. So this is an example you can kind of see here at the top that's querying for red line schedules at Broadway Station and returning a schedule which arrives at Broadway at noon. So it's querying with the map and it's returning a map. In Amnesia, that's translated into an index match against the root index on this table. The kind of underscore atom there is saying that we'll accept anything on the arrival time field, and Amnesia is returning kind of that schedule tuple underneath. We then translate that back to maps, which the rest of the Elixir code works with, and so there's a little bit of kind of overhead switching between the Erlang side and the Elixir side. Another Elixir feature we rely on heavily is the registry added in Elixir 1.4. It's scalable key value process storage. We use it for pub/sub. Different parts of the system can subscribe to a topic and be notified when the data change. This is especially important for streaming data such as vehicle locations or prediction updates, which clients want as fast as possible. When a client asks for a streaming connection, we create a registry topic based on their query. This also means that multiple connections asking for the same query can share a process. That process can then register for the upstream topics it cares about and notify the downstream consumers as soon as the new data is ready. At any point, we have around 1,000 of these processes running per server, and the registry doesn't break a sweat. So the Beam isn't necessarily the right choice if you need straight CPU power, since it is running in a virtual machine. But if you work with the Beam, you can get great performance and still maintain kind of the other benefits we were talking about earlier. This allows us to use smaller CPU instances and save money on hosting costs. If you're used to kind of other garbage collected languages, there's some important differences to be aware of. Instead of having a global garbage collection step, each process is garbage collected separately. Data is usually passed by copies so that each process owns its data, allowing each process to be garbage collected independently. However, larger binaries, like a lot of what we work with, more than 64 bytes, are stored off the heap and are passed by reference. So this saves a lot of time relative to copying all of that data between processes as it's transferred. However, it also means that multiple processes can maintain a reference to that data or a slice, keeping it around longer than you expect. If you don't want to keep all of that binary data around, you want to create a copy so that the larger binary can be garbage collected. This is especially important for us because we're storing the data in long-term storage like Amnesia or ETS, and that'll basically keep it around indefinitely as long as it's in the table. Hibernation is another kind of useful feature that the VM provides. It runs a garbage collection sweep and puts the process into a low memory state. This can be very helpful if the process doesn't receive a lot of messages. For example, if it's owning an ETS table or only doing occasional processing. We use it, for example, for the processes that are maintaining the schedule tables and long-running client connections that don't have a lot of work to do. And so when they're done with what they are doing, we can hibernate them, and then they use very little memory at all. And none of these kind of performance features matter at all if they aren't actually improving the performance. So how do we know that we're actually doing a good job? Erlang's built-in timer module is a great place to start. It calls your function and returns the number of microseconds it took to run along with the result. I've been working with Elixir for more than 4 years now, and I'm still often surprised by what parts of the code are slow. And this is just an easy way to check your assumptions. Once you're trying to do a more complicated thing, we often reach for flame charts, in particular the eFlame Erlang module. Built on Erlang's trace module, eFlame creates a flame chart like this, kind of for all the functions that are being called. Taller flames are deeper call stacks, and wider flames run for longer. It's a great visual overview of what your code is doing and can help drill back down into more specific functions. And then in production, we rely on Splunk very heavily for log aggregation, building dashboards, and that kind of thing. And Heroku's ehmon module lets us log metrics like memory usage, the run queue, and scheduler percentages, along with the rest of our data. These tend to be pretty coarse measures of performance. They're not as detailed as the ones I was talking about before, but they help us keep track of the performance kind of across the whole system as we develop new features. So what have we learned about Elixir at the MBTA after kind of building this API for nearly 4 years? So one, functional programming plus the OTP process model are a great combination. They let each process focus on one thing without worrying much about whether another process is going to interfere with what it's doing. Two, there's a great community around Erlang and Elixir, and we get to benefit from both of them, since packages can be used from either Elixir or Erlang. We get the best of both worlds when we're building our Elixir applications. And the performance is great out of the box, as I was saying earlier, and by paying attention to things like memory and scheduler usage, we can scale up to the millions of requests that we're serving every month. So thanks for listening to me talk about the API. You can reach me at Paul Swartz on Twitter or GitHub. Reach out to me at the MBTA. And all of this stuff, including the code and all of our documentation about the API, is on the MBTA's website, mbta.com/developers. And with that, I will turn it back over. If you have any questions, I think we'll do them all at the end, but you can post them. You can post them now.
Perfect. Thank you so much, Paul. Yeah, as Paul mentioned, we will be taking questions at the end, but we do recommend you submit them now either on the GoToWebinar platform or on Twitter. So any questions about the API, get them through to us now. Our second speaker for today is one of the software engineers at MBTA, and I'll introduce him now, Eddie Maldonado.
Hello. Hello, everyone. Thank you for joining us. So I'm going to talk today about the MBTA's real-time subway data and how we generate it and how we get it to riders. So a little bit about me, where you can find me. I'm a software engineer at the MBTA. Been here for a little over a year, closer to a year and a half. So what is it exactly that I work on? So basically, we maintain a series of applications that take in information about where trains are in our system, use that information to generate predictions, and then display those predictions in a useful fashion to riders. As for instance, on these LED screens here you see in this photo in one of our stations. So a little bit of background. So as Ryan mentioned earlier, yes, we have a subway system that has a few conventional metro heavy rail lines and also a couple of light rail lines. We have, not right now, unfortunately, but on a good day, over 640,000 daily riders on the system. And all of the heavy rail stations and most light rail stations are equipped with LED signs and a PA system for providing real-time information that those hundreds of thousands of people every day use to know when their train is going to be showing up. So how do we what are we starting with here? What's our sort of input that we're working with? Well, we don't really have, we have location information, but it's not really this sort of continuous location information that you might be used to in other sort of application areas. We primarily know about where trains are based on input from the signal system. And signals detect occupancy of discrete track circuits that can only be occupied by a single train at a time. So rather than knowing like a particular continuous location train can be, we know that a given train is at one of a certain number of track circuits throughout the system. There are typically several of these between each station. On some of our above ground light rail parts of the system, we actually use GPS for vehicle tracking, but we actually divide that up into geofences. So in practice, it's conceptually the same. And kind of underlying all of this, there is a graph representation of these locations and which locations are adjacent to each other's. We don't directly deal with the hardware side of things, so either the signal system or the GPS. Rather, we get a feed of data from the system in our control center that handles all of our like lower level tracking and dispatching. And so it's our job to take that and produce the rider facing information. So how do we do that? As I mentioned, there are actually kind of several different applications that play a part in this. The key one of which being what we call RTR, or Rapid Transit Real Time. This is the main app that receives live information on train locations, schedules, and any real-time alerts. So for instance, if there is a situation either planned or unplanned, causing a partial suspension of service on a given line, we know not to predict the trains will go there. Based on that information that we receive, we maintain internal state, kind of an internal programmatic representation of what the MBTA subway system looks like at the moment. And then about once per second, we crunch some numbers to produce the GTFS RT formatted output. And so that then feeds into the API that Paul was just talking about. So you can query our API or get our GTFS RT file. And from there, get our real-time predictions, the same as you would see in our stations. But in addition to that, as I mentioned, we have a system of LED signs and PA systems in most of our stations. So for running that, we have another application that we refer to as real-time signs. So we, again, kind of similar to the input, we don't actually directly interface with the hardware, but there is a separate system running these signs that receives HTTP requests to control both textual and audio output over the PA. So real-time signs pulls in these predictions from RTR. For each sign, it determines the content to display. And we also have pre-recorded audio messages to go along to provide audio equivalents for our sign content for accessibility reasons. And so then based on that evaluation of what content to display and whether or not it has changed since the last tick, we send HTTP requests to the server running the sign system, telling it to display given content on each sign around the system. So with all of that in mind, I kind of want to drill a little bit deeper down specifically into RTR, because that's kind of where a lot of the most complicated state of the system lives. And I want to talk a little bit about how it works and why Elixir is good for this use case. So I mentioned that we store internal state in RTR, and some of it's sort of some kind of obvious stuff. So for instance, we're given, we have a state representing vehicles and information about that vehicle, like some identifying information about it. Obviously its current location, things like that. To provide kind of another example of another piece of state that we need to maintain to make our predictions, we keep track of what we refer to internally as segments. So I mentioned earlier that there's an underlying graph representation of the locations where trains can be. And so we keep track of the history of how long it takes trains to move from one location to another. And so we keep track of that history in a particular part of the state. And we use that information then when generating predictions. Specifically, we look at the most recent several times that it took to traverse the segment, and then to produce our predictions, we sum those across the intervals between stations. So we need to, this particular piece of state, we need to keep it updated on certain inputs, namely as trains move in this particular case. And we need to also be able to quickly and easily reference it when we're making predictions. And then there are several other pieces of information. I already mentioned vehicles, schedule data, so that we know that for a train at a terminal when it's scheduled to leave, alerts, and so on. And so at the end of the day, we end up with this rather kind of complicated looking graph. So what this is right here, so each of the, generally speaking, each of the vertices in this graph is a gen server tracking state of one particular part of the MBTA subway system. And the arrows indicate a call from one gen server to another. So you see, kind of mostly focused on the left-hand side, there are a lot of state processes that receive updates from the OCS.buffer process that kind of takes care of receiving the inputs from the dispatch system, parsing them, and determining what updates to the state need to happen. And then if you look to the right a little bit of that, there is the GTFS real-time creator state, which is the process that once per second comes in and actually generates the predictions and writes the output to S3. Sort of another perspective we can look at, this is the supervision, the actual supervision tree rather than the call relationships. So we take full advantage of the fact that we can have nested supervision trees of different parts of the application. So kind of going along with that, so what about what about this is makes it particularly nice to use Elixir? So as I mentioned, we have lots of largely independent bits of state, and so it's easy to have a single gen server for each piece of state that is responsible for keeping track of its respective aspect of the system. Similarly, the real-time signs application, each individual sign throughout the system gets its own process, and these are easy to manage. Again, going back to some of what Paul was saying, functional programming, it's great that we can have these sort of individually tracked pieces of state, but the process of actually producing predictions is this big operation that takes as its input the overall state of the system and produces as its output the overall predictions for the system, and that code can be kept cleanly independent of the code that actually takes care of updating the state based on inputs. Again, we also have access to a lot of very handy Erlang features that we like using, especially in the science code. We use a lot of ETS tables for bits of information that need to be globally accessible. There's a built-in digraph library in Erlang that we found is perfectly suitable for the underlying graph representation that I was alluding to. And in terms of maintaining reliability, as I mentioned, this is a system where we have over 600,000 people per day riding, and these signs are prominently placed in many of our stations, and people see them and rely on them. And so we're able to build our supervision tree and have an easy model of okay, which process restart and under what circumstances if something crashes, and have confidence that a lot of kind of more minor issues won't bring down the system. With all that said, so I kind of went over a couple of the larger applications that we maintain, but we kind of cut across a lot of different parts of the Elixir ecosystem, and we maintain some smaller kind of internal use applications that show off some interesting stuff as well. We have these signs and stations. We also have developed a web front-end tool that allows our internal operations users to see what's currently being displayed on those signs. So our application, in addition to sending the requests to the actual server that drives the live signs, sends a copy of those same requests to this Signs UI application, which is a Phoenix web app. And that allows our operations users to look in and see in real time what information is being displayed to passengers. And Phoenix channels and the React front end that we have make this a very easy application to build and maintain. Another Phoenix web app we have is our prediction analyzer tool. which also uses a Postgres database that we access via Ecto. So this is the tool that we use to kind of keep track of how we're doing. We pull in our predictions every minute, and then we also pull in information about actual train arrival and departure times, and then grade them against a metric we have about which predictions count as accurate or not, depending on the combination of how far off our prediction was versus how far off in the future it was for. So there's a harsher penalty for being off on a prediction that's supposedly for 3 minutes away than for prediction that's supposedly 20 minutes away. And the web front end lets us kind of drill down into that and explore how we're doing on our metrics and compare our production and development environment for evaluating features under development. And so that is MBTA Subway Realtime. So with that, I would like to wrap it up and hand it over to, I believe, Matt, who will be our next speaker.
Perfect. Yeah. Thank you so much for that, Eddie. As Eddie mentioned, Matt will be our next speaker. Just a reminder that if you have any questions from Eddie's presentation, please put them through real time on Twitter and here, and then at the end we'll ask all your questions. Without any further ado, over to Matt Shanley.
Super, thank you. Thanks for having us today. I'm going to switch gears a little bit, and I'm going to talk about the bus side of operations here at the T. So just to let you know where I'm coming from, I'm also an engineer here at the T in the Customer Technology Department. And the plan today is to talk about, first go through a little background to let you know kind of how things work and why we started building this app I'm going to describe. Then I'll show you that app, and finally we'll talk about a lot like Paul and Eddie have said, why Elixir works really great for us here. So as a background, this isn't even the whole map, but this is the map for our system. This is the central area. It's big is the main point. We're known for having the first subway in America, but we also have a bus system that's extensive and very crucial to a whole lot of areas in our region. So we run 218 bus routes, and on weekdays they make 450,000 trips a day, covering 44 cities and towns. So it's quite broad region we serve, and it's very important to a lot of people. So we came into this wanting to improve that service. We'll talk about the details a little bit more as we go on. So our first primary customer is our bus inspectors, who are the front line of managing service for us. We have over 150 of them out there. Often they are going to be based at a train station. Some of them are mobile and other things too, but a lot of them are at train stations. That's where customers often see them. And so this might be like the end of a subway line, and at the station there could be multiple bus routes that start and end at the station and go off into different neighborhoods. So this inspector here will be managing all of those routes and all the buses on them and trying to maintain good service. So the bus driver is focusing on serving the customers and driving the bus, and the inspector is the person who has a little bit of a larger picture, but is still boots on the ground, seeing everything. And you can also see they're not in front of a desk. They're not in an office somewhere. They're in front of the customers. They are helping people. They are very present and an important part of serving the community here. So they have a lot of distractions, a lot of things they're doing. And so serving them and giving them tools to help them where they are was really important. So we say we want to improve service. What does that mean? Riders think about bus routes in two different ways, generally. If you have a bus that comes through maybe your quieter neighborhood, maybe it's going to come every 20 or 30 minutes or something. For a bus like that, you're going to probably look at an app, look at the schedule, only go to the bus stop when you know there's a bus on its way. The other form of bus service is on a main corridor, like you'll see in this picture, where buses come very frequently, maybe every 5 or 10 minutes for each route. So for those buses, customers tend to treat them much more like a subway, where they might look at an app, but a lot of times they're just going to show up and just know that, I'll be out here a few minutes and a bus will get here. So they have a little bit of different expectation there. So there are that makes two ways we have to manage the service. So the more you're at the schedule end of the spectrum, it's important to maintain, that schedule and make the buses run on time. And you can't lose track of that when you're a more frequent service, but you also want to manage towards headways, which this illustrates. Basically, you want buses coming at an even pace. Like at the top here is the better side. So, if you wait 5 minutes for one bus, you'll wait 5 minutes for the next bus. If a bus comes too early and it came 2 minutes after the bus in front of it, maybe the bus behind will come 15 minutes later, and that's, not a pleasant experience for the rider. So this is a tool that people had before we started the Skate app. It's still in use in the dispatch center, where it serves a little bit better. It's very complicated. It's okay. So what you're looking at here are, they call them route ladders. So this is a kind of summarized snapshot of each route. You're seeing some key stops, but not all the stops, and the buses are circling around. So it's very dense. It's very information rich. It takes a little getting used to for the uninitiated, but for people in these jobs, this is actually a very good interface. They tend to like it a lot because you can see the apps kind of intuitively. You can see the state of things for a whole bunch of routes at once in one screen. So that's the good part about it. The bad part from our perspective especially for the inspectors out in the field, is this interface is dated. It's on to get into it, you get a VPN into a desktop computer. And so if you're out in the field, that doesn't work so well to begin with. And then there are all kinds of things, like a lot of interactions on this tool start with a right click, which on mobile is not such a great thing to have to deal with. So this is what inspectors used to have out in the field. Some of them, it was old, it's hard to maintain, it didn't work very well, it's not very intuitive, it's hard to right click. And so a lot of people just didn't use stuff like this. This was actually a better solution for a long time, and we still use paper a ton, so that's never going away. Paper is really useful. So this was the state of the art a year ago. So we were trying to come up with how can we improve the situation for them? How can we give them these ladders, these tools that we know are very useful for the job, but in a way that's friendly for where they are? And two last factors, the data needs to be up to the minute to be useful. I want to know where the bus is now, not where it was 5 minutes ago. That's pretty easy to understand. And then finally, this is a critical tool. If if they're using it to do their job, it better be working. So so we took all this input, we did a lot of user research, and that continues, and we came up with this app that we call Skate. There's not a really good story to the name. Basically, it was an internal name that we don't have a marketing team, so it escaped the lab. So this is a web app. Most of our inspectors use it on tablets, but it is not exclusive to those. You can load it in your desktop computer, you can load it on your phone. It works anywhere. It's just a website, though on a tablet or phone, you can save it to your desktop and kind of pretend it's an app. It works that way. On the server, it uses Elixir and Phoenix, and on the client side, it's a React single page app. This is what it looks like. So you can see that the route ladder concept is here. It's still the primary focus, but the interface is a little bit more modern looking. So each of these triangles is a bus on the route going around, often up one direction and down the other, but not always. So at the bottom, you'll see them coming around the circle, or they're coming in from a different work, or coming on for the start of the day, that sort of thing. You can see, like in the old software, you can see a lot of information at a glance, which is really important. And then we've color coded the vehicles. So the green ones are on time within our definition of our expectations. The red ones are early and the blue ones are late, which is sometimes counterintuitive at first, but from the rider perspective, if your bus is supposed to show up at 12 o'clock and you get there at 12 o'clock, if it shows up a minute later, you're a little annoyed, but it's okay. If it showed up at 11:59 and you're down the block watching it go by, that's a really bad experience. So early is worse than late in this case. And finally, those lines there pointing to the gray, that shows where the bus is pointing to where the bus is scheduled to be at the moment. So you can have an idea of how late or how early it is. And last, over on the right there, you can see a little Pac-Man ghost. That is a trip that is scheduled to be running that is not running. So, you know, someone calling sick or a bus broke down, whatever the case may be, there's supposed to be a bus there serving customers and is a gap in service. So that's one of the key roles of these inspectors, is handling situations like that come up frequently, and doing what they can to move people around, adjust things, but basically fill that service for our customers. You can also zoom in on a vehicle and see more information about it, including a live map of, you know, you can watch it go down the street in real time, and see just more details about the trip and the work that's being run. There's also, it seems very simple, but there's a little directions link that is just a link to Google Maps, but especially for inspectors who are mobile, who are in cars, who, if a bus breaks down, they need to get to it, this link was huge for them. It was a big lifesaver. So it's funny, sometimes the smallest features are the biggest wins. We also have, sometimes we need to run shuttles that don't have scheduled service, and it's hard to show route ladders or things like that because there's no schedule to adhere to. So we have some other tools just to like generally see what's going on in some way. So this is a map where you can just see, you know, vehicles moving around the city, and you can see the shuttle route they're supposed to be driving on. So you can at least get some kind of information on. And finally, there's a search feature, so you can look up by an operator, a bus number, the work they're running, and find out where folks are if you just trying to dig into something. So that's what the tool is. And if, you know, from traditional web development, you know, I've been doing this for a couple of decades or something, and this kind of seems like a daunting amount of work maybe in the traditional way we built web apps. But I think the number one reason that I think Elixir and Phoenix are awesome is because this app is actually relatively simple, and I like it that way. So we can use a lot of out-of-the-box features that Elixir and Phoenix give us, and get a lot of things for us. So don't worry too much about this diagram, but this is how we load data in. This gets back to what Paul described earlier, that there's two types of data. There's scheduled data, so that's the left side of this, that we just load once and keep in memory. So that just when the server starts up, it processes all that and then just keeps it there. And then on the right side is real-time data. So there's several different sources we had to look to get this, but this is the, you know, all the information about every second where the bus is and when it's predicted to be the next stop and all that sort of thing. So we have a few different sources, we pull them and we merge all that data together, and then we push that out to the client. screaming at it. So so those are the two data types. And for this app, it might be useful to know that all of our data is read-only. So we have other places that we look for all the truth of where the data source is. So so we are just taking data in and presenting it. So here are several things that we get from Elixir that do a lot for us. So the first is pretty simple, Gen servers. We load, I don't expect you to read it, but this is one of our CSV files on the left of scheduled data. So we parse all that in, and then it's not small, it's a few gigs worth, but it can live in memory. So we can just have that, we don't need a database or anything. We can just serve that up as we need it and query it the way we need to. And then second, GenStage is maybe a little less familiar, but it's super powerful. It does a lot for us. So as we're pulling in these real-time data sources, we get little bits that might hold different types of information. One piece might get the trip that's being run, another piece might get the prediction, and another piece might get the GPS coordinates, and we need those all to be associated with the same vehicles. That we merge them all together. So we use GenStage to manage that whole pipeline. And that's great for us. And then PubSub to get that out to the client. So, and then for that real-time data, similar to what Paul and Eddie both described, we use ETS tables that can just live in memory. As a new client joins the server, someone logs into the app, they can see immediately the real-time data because we are just having it waiting for them. So they don't need to wait till the next update, even though the next update is going to be a second or two later. And so we push all the live data out through Phoenix channels, which is super handy. We use registry also that Paul mentioned to keep track of subscriptions from the clients. But channels took care of a lot of things that might be a pain in the butt, and made it very easy for us to subscribe to real-time updates and have them pushed to the client. And finally, for everything we do, getting back to the importance of this tool and the downtime not being acceptable, the supervision tree that Elixir Erlang gives you is super critical. So, you know, we get updates of real-time data maybe every second or two, something like that. If there's an error, something goes down, you miss one of those, but it gets rebooted, it comes back, and a second later you get a second update, that's no big deal. No one even notices. If, however, the whole app goes down and you don't have information that you need to do your job, that's a much bigger problem. So this inspector here, that's the face we like to see from our users. So finally, this is a work in progress. This represents a year. We're just about to a year anniversary of starting work on it. It's been mostly 2 developers on the team, just to give you a sense of progress. We had a prototype working in 3 months and being used somewhat, and then like a full, pretty strong MVP out in 6 months, I believe. But active development still continues. We're working on more in-depth schedules so people can see what's this driver doing next in their day, what's this bus doing next in the day. Those are often not the same thing. So there's a lot of detailed information we can get to folks. So that's coming up soon. So that's it for me. And I think we can take questions for all of us at this point.
Yeah, thank you so much for that, Matt. I will open up for questions. Just give me 1 sec while I unmute everybody in the room and make it so that you're all able to answer where you feel relevant. Okay, perfect. So thank you so much, everyone, for your presentations. We do have some questions coming in. The first of which is one that we get a lot ourselves, which is, how does using Elixir impact your recruitment of engineers and developers?
Yeah, so this is Ryan. it's pretty interesting. I think if a developer has previous Elixir or functional programming experience, it's perceived as a major plus. People really love it, and they want to work with it. Of course, many people are not familiar with it, and I think for people who are not familiar with it, I've not perceived it as like sort of a major turnoff. More of something they're curious about. They want to know, like, if they do end up getting hired, what resources they should read. So yeah, I think it's interesting. I think I view it as a net positive.
Cool. Thank you for that. A quite linked follow-up question. What have you found the learning curve to be for new developers to the language at MBTA?
Paul, you want to field this one?
Sure. Yeah, I think it's been it's very easy for developers to get started. Most of the people that we're seeing, if they don't have experience from Elixir, have experience with Python or Ruby or something where like the syntax feels pretty similar, and so they can get up and running on updating Phoenix templates or implementing new functions. We have people shipping PRs their first week. It's the kind of, how do you model larger features? How do you use processes and supervision trees? That tends to be more like on the job learning, and that takes a little bit longer, but we haven't had any problems with getting developers up to speed. I don't think Eddie or Matt, I don't think either of you had worked with Elixir before joining customer technology, and here you are kind of like leading big initiatives here that we're building. So
that's fantastic. Really cool to hear. Another question we have had come through is, are vehicles in your system treated as processes or as separate sets of data?
Eddie or Matt, do you want to take that?
Yeah, I mean, like at least, it's going to depend on exactly which application you're talking about. At least in R, on the subway predictions side of things, they're treated as pieces of data rather than each getting a separate process. I'm not sure exactly what skate or other parts of bus real-time stuff do.
Cool. Another one we've had come through is, since there's so much held in memory, storage, and state, what would a full cold restart of the system look like?
I can say for the bus side of things, the Skate app, the scheduled data is a little bit to load up. We have not worked to optimize it because it hasn't been priority, but it takes about 2 minutes. Though in development, we save that in a cache. So practically, as far as we're doing our development work, it's a second, maybe, if that. So it's not an issue there.
Mm-hmm. Yeah, on the subway real-time end of things, we do, I didn't really go into it in my presentation, but we do use the Erlang binary to term and term to binary functions to persist the state of the application just to an S3 bucket and reload it on startup. It's a pretty simple solution, but it works all right. And so when we do a deploy, or if there's a crash or something, we can restart from a recent copy of the state.
Cool. This is the kind of question we love to see after a webinar, so thank you. It's a great sign that people were engaged with it. It is, picking a language for such a large important project is hard, and it's even harder when the language is as exotic as Elixir. How did you manage to get your decision past the business? Were there any objections to using such a niche technology? And do you have advice for any others facing the same uphill battle?
Yeah. So,
since you were there, I think it's a good one for you.
I can definitely talk about this a bit. I think the advice I would have is the people that you are you're needing to convince, so like for me, I needed to convince our CTO at the time, who was, skeptical to kind of say the least about it. But those people have networks of people that they know. And so if you can figure out who in their network is on board with Elixir. So for us, and for me, it was other, Boston area technology folks in both like the agency world, but also in some like private companies, were starting to look at Elixir as options for new projects that they were spinning up. And that kind of gives them, when my boss can say, it's not just, my employees who are saying this, it's other people in the technology community who are at my level in other companies are also looking at this. It kind of gets you that buy-in. The other thing that really helped for us was building prototypes. So we built, for the API, we built a prototype in Elixir, a prototype in Python with Django, and with Ruby on Rails. And in terms of just like out of the box, like how does this perform? How easy is it to work with? There's kind of like no contest that Elixir was certainly for that project the right choice.
Perfect. Thanks.
I'd like to add to what Paul said and say that, when you're in charge of the technology for a team, a big concern is how you manage risk. And I would say that although Elixir itself is relatively new, obviously the sort of underpinnings are not. And there's a lot in there that helps an organization or a team manage their risk. That's pretty unique to Elixir and I guess Erlang. So that's probably another aspect that can be emphasized when you're trying to make the case.
Perfect. Thanks so much for both of you for that advice. We hope that you, Marco, who asked the question, are successful with that uphill battle. We have 2 more questions that we will take, and then we'll wrap up. The first one is, do you have any advice based on what has worked for your team on deployment, containerization, and Kubernetes?
So we do run pretty much all, probably I would say 90% of our Elixir applications are in Docker containers. They're not on Kubernetes. We are using either ECS on Amazon or Elastic Beanstalk also on Amazon. And running Elixir and Docker containers has been great for us. We do a handful of kind of like on-prem instances where we're just kind of running it on individual servers. I would not recommend that as much, just because we get a lot of benefit from having our applications in containers in terms of scaling and deploying to new environments when it's in a container. But certainly Elixir and Erlang do provide a lot of kind of ecosystem around like hot upgrades and stuff like that that you can benefit from even on a single server.
Cool. Thank you for that. And the last question we'll take is, someone has asked, you mentioned React single page app on the client side. What informed the decision to use that as opposed to Phoenix?
For the Skate app, we knew it was going to be a very dynamic.
I can take this one. We do use Phoenix in probably. Oh, sorry, Matt. I think we jumped in at the same time. I could give like a general answer. So we do use Phoenix templates for probably most of our applications. React we found to be really good on interfaces that are very dynamic. Obviously, it's sort of what React is designed for. Although I guess you could say that Elixir doesn't have anything special for React, neither does Python or Ruby or PHP or whatever. So we found it to be easy to use React in sort of the normative use cases where you have a user interface that is really being updated frequently with real-time data or user interactions.
Perfect. Okay, that is all we've got time for today. I would like to give a huge thank you to Ryan, Paul, Matt, and Eddie for what I'm sure you'll all agree has been a really fantastic and informative webinar. As always, we will be sending a recording of this webinar out to all registrants in the next week, so please keep an eye out on your emails for information about that. One other thing I'd just like to plug, or two, firstly, our meetups obviously have all gone virtual at the moment, which means that regardless of where you're based, you can attend our meetup next week on April the 2nd. You can find more details about that on the London Beam Users Group meetup page. And secondly, just a reminder, as stated at the start of this webinar, MBTA mentioned they are always sort of looking for Elixir talent. So if you are in need, please do hit them up and see what happens. Thank you so much again for joining us, and thank you for presenting.
Thanks,
Thank
everyone.
you.
Thanks, everybody.